What's up, guys? Welcome back to another session of system design. And today we are going to discuss about hotel booking system like Expedia, Booking.com, or Agoda. So when you open Expedia, you search hotels in Paris, check in July 14, and within a second, hundreds of results come back. You pick one and you book it. A confirmation email lands in your inbox. And that sounds simple, right? But here's what actually happened under the hood. Your search hit a geo-indexed database across dozens of properties. A pricing engine ran dynamic pricing rules in real time. The system held that room for you while you entered your payment. Your card was authorized but not charged yet. And somewhere in a database, a row was locked so nobody else could book that same room. Now that's what we are designing today, a hotel booking system like Expedia or Booking.com, one of the most deceptively complex distributed system out there. So let's get into it. Let's start with what the system needs to do. First is search. Users need to search for hotels by location, date, range, number of guests, filters like price, star rating, amenities. Search needs to be fast. We're talking about sub-second. Second is the inventory management. The system must know which rooms are available for which dates. This is not trivial. A hotel has multiple room types. Each room type has a count, and the availability changes by the minute. The third is the room reservation and booking. A user selects a room, the system holds it, then pay, and then the booking is confirmed. The hold must be temporary. If they don't pay in 10 minutes, the room goes back to the inventory. Then the fourth is payment processing. We need to authorize a card at booking time, capture the payment later, typically at check-in or few days before. We also need to handle cancellations and refund. Then the fifth is the pricing engine. Hotels do dynamic pricing. A room that costs $200 on Tuesday costs $400 on a Friday in peak season. The pricing engine needs to evaluate rules in real time. Then the sixth is the loyalty point. If you have rewards membership, your points need to be calculated and applied at checkout. Then the seventh is the notification, booking confirmations, reminders before check-in, cancellation notices, all via email and SMS. So to summarize the functional requirement, hotel and room search with geo and filters, real-time room availability check, temporary hold on booking confirmation, payment authorization and capture, cancellations and refund flow, dynamic pricing engine, loyalty points accumulation and redemption, and the notification. Now let's talk about the non-negotiables. Availability. The system needs to be highly available. People book hotels at all hours. Downtime means lost revenue. We are targeting 99.99% uptime. The consistency for booking. This is critical. We cannot double book a room. If two users try to book the same room for the same dates at the same time, exactly one must succeed. The other must get a clean error. This requires strong consistency for inventory and the booking layer. Then eventual consistency is acceptable for search results and pricing display. If you see a slight stale price for a second, that's okay. But if we confirm a booking, that must be immediately consistent. Then we talk about the latency. If for search, the search should function under 500 milliseconds. The booking confirmation should function under 2 seconds end to end. The price lookup should be under 100 milliseconds. Then we talk about the scalability. Expedia handles over 3 million bookings per day. During peak holiday season, the traffic spikes 10x. We need horizontal scalability at every layer. The durability, a confirmed booking must never be lost, not even if a data center goes down. Then the security. Payment card data must be a PCI DSS compliant. We never store raw card numbers, we tokenize it. All right, so let's do some back of the envelope math. Assume 100 million daily active users browsing. The conversion to booking is about 1%. So a million bookings per day. That's roughly 12 bookings per second on an average. Peak is about 10x, so 120 bookings per second. Then we have the search queries. Every user does about 5 searches before booking. So 500 million searches per day. That's about 6,000 search queries per second. At peak, it might be around 60,000 per second. Now storage. Each hotel has roughly around 500 rooms on an average. A major OTA like Expedia has around 3 million properties listed. 3 million hotels times 500 rooms times 365 days of availability data. That's a lot of inventory rows. So let's simplify. Per hotel, we have room availability table indexed by room type and date. Now that's manageable per hotel. But at scale, we are talking about hundreds of terabytes of availability data. Then we have the booking history. 1 million bookings per day, each record are roughly 1 KB, that's 1 GB per day. 365 GB per year, growing infinitely. We archive core data to cheaper object storage. Now, one more thing on reads versus writes. Reads dominate the system. Their searches, availability check, price lookups, these are all reads. Writes happen at booking time only. Read to write ratio roughly around 1000 to 1. This heavily influences our architecture. Guys, let's define the core APIs over here. We have the search APIs. It is a get API with city parameter. We write the check-in, check-out, number of guests, filter, sort, and the pages. It returns list of hotels with summary, price, availability flag, and rating. Then we have a check room availability API of type get. This returns the available room count, price breakdown per night. Then we have a create reservation hold. This is a post type API. It returns the hold ID, expiry time, and the total price. And then we have the confirm booking. So once we do a post API for the confirm booking, we pass the payment token, loyalty points redeem if available. It returns booking ID, confirmation number, payment status. And then we can also have a cancel booking, which is a delete operation, and it returns the refund amount and refund ETA. Now let's look at the data model. So we have a hotel table, which has hotel ID, name, description, address, lat long, star rating, amenities, and created ad. Then we have the room type table in which we define the room type ID, hotel ID, name, description, capacity based by amenities. Then we have the room inventory table. This is the most important table because we have the inventory ID, hotel ID, room type, ID, date, total rooms, booked rooms, and the held rooms. For each hotel and for each room type, for each date, we maintain a count. So available rooms is equal to total rooms minus booked room minus the held rooms. Now, this table needs very careful concurrency control. Then we have the reservation table in which we have the reservation ID, user ID, hotel ID, room type ID, check-in, check-out status, which can be held, confirmed, cancelled, expired. Then other fields like hold, expiry, total price, dated at. We'll have the payment table, which stores the payment information. Along with that, we will have the loyalty points table, which will have the loyalty points for each customer. Did you notice how I separated hold from confirmed booking? And this is intentional. A hold temporary decrements the available inventory. A confirmed booking is permanent. An expired hold returns the room back to the pool. After this, let's look at the overall system architecture. We have several major subsystems. The search service handles the hotel discovery. It talks to the search index, not to the primary database. The availability service is the source of truth for the room counts. It is strongly consistent. The booking service orchestrates the reservation flow. Hold, payment, confirm. The pricing engine computes real-time prices based upon the rules. The payment service handles authorization, capture, and refund with the payment gateway. The notification service sends email and SMS. The loyalty service manages the points. Now, these services talk to each other, but we need to be careful about the synchronous versus asynchronous communication. For the booking critical part, search, availability check, hold, payment, confirm, these are synchronous. The user is waiting. Now, for the non-critical part, sending confirmation email, aborting loyalty points, syncing analytics, these are asynchronous via message queue. Now, let's trace our booking flow. First, the user searches. The request goes to the search service, which queries the Elasticsearch index, results the comeback. Then the user selects a room and checks its availability. The availability service checks the inventory table for that hotel, room type, and date range. Then user clicks book. The booking service creates a hold. It atomically decrements available rooms in the inventory table and creates a held reservation record. Then the user enters payment. The payment service calls the payment gateway to authorize the card. No charge yet, just a hold on the card. Then user confirms. The booking service flips the reservation to confirm. The payment service captures the charge. The notification service sends the confirmation email asynchronously. If the user abandons after 10 minutes, a background job scans for expired holds and releases the inventory. Okay, now we'll do a deep dive into some of the components. The first one is the inventory management and double booking prevention. Now, this is the hardest part of the system. Let's say two users try to book the last available room at the same time. Without proper concurrency control, both can see the room as available, both create a hold, and we have doubled book. Now, how do we prevent this? The first is optimistic locking. We add a version number to the inventory row. When we read inventory, we get the version number. When we update, we say update inventory set held rooms is equal to held rooms plus 1, where inventory ID is equal to X and version is equal to 5. If the row was already updated by someone else, version changed, our update affects 0 rows, we retry or fail. This works well under the low contention. Then we have the pessimistic locking. Select for update. We lock the inventory rows before reading. Only one transaction can hold a lock at that time, and others wait or time out. Now, this is simpler to reason about but can create bottlenecks under high traffic for popular hotels. Option 3 is atomic decrement with a check. We use single SQL statement. We use update inventory set held rooms is equal to held room plus 1, where inventory ID is equal to X and the total rooms minus the book rooms minus the held rooms is greater than equal to 1. If no rooms are updated, the rooms are not available. This is elegant and avoids explicit lock. For Expedia scale, I'd go with option 3 combined with row level locking in the Postgres. But here's what a principal engineer would ask. What happens if the hold is created but the payment service times out? The hold is stuck in held state forever unless a background cleaner runs. And if that cleaner has a bug, you leak inventory. The fix is every hold has a strict expiry time stored in the database, a separate scheduled job or a database level TTL if you're using a different store reclaims the expired holds. You also want a dead letter queue for payment failure so ops can investigate and manually release holds if needed. The next topic we are going to discuss is about the pricing engine. Hotels use dynamic pricing. The same room can cost different amounts on different days. The pricing rules includes base price per room type, seasonal multipliers, date of week adjustments, demand-based pricing, fewer available rooms is equal to higher price. Then we have the promotional discount, the loyalty tier discounts, and last-minute deals. The pricing engine takes these hotel ID, room type, date range, user loyalty tier, and computes a final price. You could implement this using a rule engine, a set of ordered rules evaluated in a priority sequence. Or you can also pre-compute prices for the next 365 days and cache them. Only recomputing when the rule changes. But here's a principal engineer question. What if a hotel manager changes prices in real time? You need to do cache invalidation and you need the updated price to reflect in the search results quickly. In that case, the flow should be hotel managers update the price in hotel management portal. This publishes an event. The pricing cache is invalidated for that hotel. Next request recomputes and recaches. For the booking confirmation step, you always recompute price from the source. Never trust the cache price from the search time. The price shown at search could be seconds old. Next, we'll go into search with the geo filters. Hotel search is fundamentally a geo search problem. When I say hotels in Paris, I mean hotels within the same bounding box or radius around the Paris. We need an index that supports geo-distance queries, find hotels within the 5 kilometers of lat lang. Then we need to be able to filter by amenities, star rating, and price range. We should be able to sort by price, rating, and distance. We should be able to do full text search on hotel name. Elasticsearch and does all of this beautifully. We index each hotel as a document with geo point field for location. Queries use geo-distance filter combined with the term filters for amenities and range filters for the price. But here's important question. How do we keep this index in sync with the primary database? We use the CDC, that is change data capture. When a hotel's data changes in Postgres, the Debezium captures the change from the write-ahead log and publishes into the Kafka. A consumer reads from the Kafka and updates the Elasticsearch index. This gives us eventual consistency for search, which is acceptable. A new hotel listing showing up within a few seconds of creation time is fine. What is not acceptable is showing a hotel as available when it has zero rooms left. So the availability field in the search index is updated in real time, but the actual booking flow rechecks the availability server as the source of truth. Never trust the search index for final availability. Always re-verify. Then we have the component payment hold and the capture flow. Hotel payments are different from e-commerce payment. In e-commerce, you charge the card at the purchase time. In hotels, you often authorize a booking time and capture date. Now, why is that so? Because you might cancel it because the hotel wants to verify the card is valid, but they don't want to charge you until you check in. So the flow is at booking, authorize, the payment gateway puts a hold on the customer's card for a full booking amount. The money is reserved but not transferred. At check-in or a few days before, you do the capture. The actual charge is executed. On cancellation, it is void or refunded. Now, the tricky part is what if the authorization succeeds but our system crashes before saving the booking to the database? The customer cards has a hold, but they have no booking. Now, this is a classic distributed system problem, dual writes. The solution is item potency. When we call the payment gateway, we pass a unique item potency key, the hold ID. If we call authorize twice with the same hold ID, the gateway returns the same result both the times. Our booking service checks does a confirmed booking already exist for this hold ID? If yes, returns success without reprocessing. This makes the confirm endpoint safe to retry. Then the next module is cancellation and the refund flow. Cancellation policy varies by the booking type. Free cancellation up to 24 hours before, full refund. Non-refundable rate, no refund. If it is partial, 50% refund if cancelled within 3 days. The booking service needs to know the cancellation policy at the booking time. So store it in the reservation record. When a cancellation is requested, first you do look up the reservation table and its cancellation policy. Then you calculate the refund amount based upon the current date and the policy. You call the payment service to initiate the refund. Then you update the reservation status to cancel. Then you release the inventory, decrement the booking rooms back. Now award any loyalty points adjustment and then send the cancellation email. Now, this is a multi-step operation. If we crash in the middle, say after refunding, but before releasing the inventory, we have a mess. So how do we handle this? We handle this using the Saga pattern. Now, each step is a transaction. If a step fails, we run the compensating transaction for the steps that already succeeded. We use an outbox pattern here. Write the cancellation event to a local outbox table in the same transaction as the reservation status update. A separate process publishes the event and drives the Saga forward. Now, the next component is the loyalty point. Loyalty points are accumulated per booking and redeemable at checkout. The earn rate is typically 1 point per dollar spent. The redeem rate is equal to 100 points is equal to $1 discount. The loyalty service maintains a ledger. Every earn and redeem is a row in an append-only table. Now, the current balance is equal to sum of all the events for the user. Why append only? Because we never want to lose the audit trail. If a customer calls and say, where did my points go? We can show every transaction. Now at checkout, the redemption is atomic with the booking confirmation in a single transaction. We debit the points and confirm the bookings. But here's the principal engineer question. Now, what about the race condition on points? If a user has a browser open on 2 different tabs and tries to redeem points twice, what will happen? The item potency key on the redemption request check that available balance is greater than equal to redemption amount before actually deducting it. Now, what about fake bookings to farm points? Now, this is fraud detection. Here we look for patterns of book and cancel cycles within the hours. All right, so how do we monitor this? First, we talk about the booking funnel metrics. Search to availability check rate to availability check to hold rate, hold to confirm rate, abandonment rate at each step. If the hold to confirm rate drops suddenly, payment services might be degraded. Then the second is inventory metrics. Hold created per minute, holds expired per minute, double booking attempts, then failed atomic decrements. Then the third is latency matrix. We have P50, P95, P99 for the search latency. Then we have P50, P95, P99 for booking confirmation latency. And then we have payment gateway response time. Then 4 is the system health. Database connection pool utilization. We talk about Elasticsearch query latency and error rate. Then we talk about the cache hit rate for the availability summaries and message queue lag for the CDC pipeline. About the alerting, pager duty alerts if booking success rate drops below 99% or if the P99 latency exceeds the 5 seconds. Now let's do some of the tool comparison over here and the technology choices and why we will pick up each over other. If you choose between Postgres versus Cassandra for inventory, Postgres has strong asset guarantees, perfect for inventory where you need atomic decrements. Natively, it is good for select for update for pessimistic locking. Row level logging is efficient. Then the downside is it has vertical scaling limits. Sharding adds complexity. Cassandra is linearly scalable. It can handle massive write throughputs, but no native multi-row transactions. Lightweight transactions use Paxos, slow, and limited. So doing a decrement only if available is greater than 0 reliability in Cassandra requires careful use of compare and swap, which has performance costs. Now, it is better for booking history, append only event logs, where you don't need transactional guarantees. So my recommendation for inventory is Postgres for read replicas. For booking history and audit events, we can use Cassandra or a time series store. Now, here's a comparison between Elasticsearch and Postgres full text for search. Elasticsearch is used for full text and geo search. It handles complex queries like geodistance, filter, sort, facets in a single query. The horizontal sharding is built in. The downside is eventual consistency. Not a source of truth, it requires the sync pipeline. Whereas Postgres with PostGIS, it supports geo queries natively with PostGIS extension. It is good for moderate scale. Everything is in one system and simpler ops. But the downside is it struggles with combined geo plus full text plus facet of full scale. So my recommendation is Elasticsearch for search at Expedia scale, Postgres plus PostGIS for a smaller scale hotel booking site. Now another comparison is Memcached for caching. Now Redis has richer data structure like sorted sets, hashes, and streams. It is used in persistent options. It has atomic operation that like INCR, DCR. It is useful for rate limiting and hold counts. It has PubSub for lightweight messaging. Whereas Memcached, it is simpler, pure key value cache. It is slightly faster for simple get and set at extreme scale. And it is not persistent. Now for this system, we will use Redis. We need atomic decrements for availability summaries, sorted sets for ranking, and TTL-based expiry for the holds. Here's a comparison between Kafka and RabbitMQ for event streaming. Kafka is log-based. Events are retained and replayable. Multiple consumers can read the same event independently. It has a very high throughput. It is designed for millions of events per second, and it is good for CDC pipeline, audit events, and analytics. Now, RabbitMQ is a queue-based. Once consumed, the message is gone. Better for task queues with complex routing. And it is easier to operate at smaller scale. It is good for notification dispatch and retry. Now for CDC, audit trails and analytics, I will use Kafka. For notification dispatch, either works. RabbitMQ is simpler. Now let's step back and look at what we have built today. A hotel booking system at Expedia scale, which needs a strong consistency layer in Postgres for inventory and bookings, and atomic decrements with optimistic or pessimistic locking to prevent the double booking. A separate search layer in Elastic for fast geo and filter queries synced via CDC. A payment flow with authorized at hold capture at check-in and full idempotency via idempotency keys. A Saga pattern for multi-step operation like cancellation where partial failures need compensation transaction. A pricing engine with pre-computed cache prices and real-time invalidation. An event sourcing model for full audit trail and traceability. And a carefully layered consistency model. Strong where money is involved, eventual where staleness is acceptable. The key insight is not every part of the system needs the same consistency guarantee. Knowing where to draw that line is what separates a good system design from a great one. Now thanks for watching. If it was useful, subscribe to Yoda Monk for more system design deep dives. See you there.